All right, you guys. This is part 3 to the series FRQ questions. Okay. Um, yeah. So make sure that you guys have scratch paper on the side because we don't want to write all over this. So I deleted everything so that I have space. But yeah, since there's a lot of things to jot down, you guys might want to do this on a separate sheet here. Okay. All right. Here's my third highlight. I'll pick green. Okay. Error-bound questions. Usually it's the last part of your series question. So, yeah, they tend to leave the error-bound question at the very end, but again, it's not guaranteed, okay? So, remember, the reason why students score globally very low on the series question is because teachers tend to not have enough time to cover the material, but we have all the time on our side here, okay? Because we've learned all of our A-B content, so we can take our sweet time with BC, all right? Which is why we losing our generally scores super high above the global average, because we can really practice these problems. So this is where you guys can really kick butt on the BC exam, okay? So error-bound questions. People tend to freak out because of the verbiage that they use, but I'm going to show you guys that it's very easy to translate, okay? So first with the highlight, here we go. We'll start off with 2017. Make sure you guys are using different colors, okay? Okay, so error questions either will say error somewhere or they'll have some weird notation, and I'll show you, okay? So here, it's usually the last one, usually, not always, but in 2017, here they say, use the alternating series error bound to show that. Now, they were nice enough to tell us the error bound here, but this notation is actually error, and we'll talk about that in a second, okay? Remember, error refers to you have a function, okay? So you have some function. You don't have to write this part down. And then you have a lookalike, okay? To find out how close you were, the error is how far you are with your lookalike from your actual. So the way you do that is you subtract the two. You're subtracting your actual from your lookalike. Okay? Or the other way around. It really doesn't matter. And that's why there's absolute value here, because we're just talking about distance. How far are you from the actual function? Okay? That is your error. All right? So you'll see that in the next few examples here. But let's keep going. Back to our highlight. 2016. Okay? Okay, in part D, show that the approximation found in part C is within 0.001 of the exact value. Okay, so if you go back to part C, we're approximating, so that's our estimate, and we're trying to show that it's within 0.001 of the exact. So when we take our exact or our actual minus our approximate or our lookalike, we get error. That's error, you guys, okay? So they phrased it a little bit differently. So make sure you guys understand that. 2015 is not present here, okay? That's very rare. But okay, let's keep going. 2014. Doesn't seem like we have it here either, so we're going to move on. Not present here either. Okay. 2012. Okay, actually occurs in part B. All right. So how do we know that this is an error question? Okay, so let's read this here. The Maclaurin series for G evaluated at x equals 1/2 is an alternating series whose terms decrease in absolute value to 0. Blah, 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 right? The approximation for a G of 1/2 using the first two non-zero terms of the series is 17 over 120. Show that this approximation differs from G of 1/2 is less than 1 over 200. Let me translate that for you guys, okay? Show that the approximation differs from the actual. That right there is, again, error, but just phrased in a very different way, okay? Okay, so again, you guys are getting used to the verbiage, and then I'll show you how to actually do it, okay? All right, so 2011. Okay, do we have it here? Okay, so I do a quick spot check, and I can tell that it's in part D because we're trying to show that the absolute value of something minus another thing is less than something else. Again, actual minus approximate or estimate minus actual doesn't matter. When you see absolute value of something minus something, that's error, okay? Again, that's error. Notice how they didn't use the word, so it's phrased a little bit differently. Let's keep going. 2010. Okay, is in part D. Explain why this estimate differs from the actual. Estimate differs from the actual. So estimate minus the actual. So that right there is another form of error bound, okay? 2009. Not present here, okay? 2008. Use the series found. Was part D such that? Oh yeah, right here. Okay. Right here. You're taking the absolute value of some difference. Okay. Good. 2007. Explain why the estimate found in part C differs from the actual value. That's error. Okay. And that's it. All right. So it appears pretty often, enough for us to want to practice. Okay. So here we go. We'll do as many as we can. Whatever I don't cover will be your practice. Okay. But then you could also still reach out to me. All right. Here we go. So use the alternating series error bound to show that P sub 4 of 1/2 minus G of 1/2 is less than 1 over 500. There's a lot of notation, and people can tend to get caught up in that, okay? All right, so let's read the whole thing. Part D, let P sub n of 1/2 represent the nth degree Taylor polynomial for G. About x equals 0, evaluate it at 1/2, where G is the function found in part C. Okay, so I'm going to have to go back and let me look this up real quick so I don't have to reinvent the wheel here. 2017 BC. 17 BC scoring guidelines. Okay. Okay, so in part A, we have the series right here, okay? And the general term. I forgot what it was. It's not in front of me. But in part C, they tell you to integrate F, which is where you would just integrate each term. I'm going to write it out here. You should end up getting x squared over 2 minus x cubed over 6 plus x to the 4th over 12 minus x to the 5th over 20 plus dot 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 negative 1 to the n plus 1 x to the n plus 1 all over n plus 1 times n. Okay, so Again, don't worry about that part. If you have a question in part C, you can reach out to me here, okay? I'm just borrowing the answer right now. So this right here is g of x. It's equal because we keep on going forever, okay? Now, the nth degree Taylor polynomial, they only want us to go up to 4, where n is 4, okay? And n is referring to the 4th degree, okay? So p sub 4 of x is going to be x squared over 2 minus x cubed over 6 plus x to the 4th over 12. So again, we're only going up to the 4th degree there, okay? So notice how we use the first, how many terms? We use the first 1, 2, 3 terms. That's 3 terms right there, okay? Okay. You noticed that it's alternating, okay? And also they were nice enough to tell you to use the alternating series, okay? But even if you didn't get that, you could tell that the series alternates, so you want to use the alternating series error bound, okay? So here's what you guys do. You're going to say that p sub 4 of 1/2 minus g of 1/2. That you just bring down. It doesn't matter what that is. What matters is what goes after here. Remember, your error is going to be based off of the next term, okay? So since we use the first 3 terms, okay, the error is going to be based off of the next term, which is this one right here. So that's going to be the absolute value of negative x to the 5th over 20, okay? Evaluated at 1/2, because right there. All right, so here we go. So p sub 4 of 1/2 minus g of 1/2, again, when you're subtracting the actual from the estimate, that's just error, is going to be less than. The absolute value of a negative will make that go away, so that's just going to be 1/2 to the 5th power over 20. Okay, and this is where you guys can kind of cheat a little. Here we go. Equal is equal, okay? We have to show that it comes out less than 1 over 500. So you could just say, which is definitely less than 1 over 500, and then you're done. Okay, but let me just show you guys the work that you don't need to do. This right here is the same thing as 1 over 2 to the 5th times 20, okay? Which is the same thing as 1 over 32, is that 32? 2, 4, 8, 16, 32, yeah, times 20, which is the same thing as 1 over 640, which is definitely less than this, but we don't need to do that. You do have to state that it is less than 1 over 500 though, okay? So if you think about this here, the only work that needs to be done, I'll highlight it in yellow here, is pretty much this and this. And that should earn you about 2 or 3 points right there. It looks really complicated, but past the notations and past the verbiage, actually finding the error is super easy. Okay? Cool, let's do another one. Okay, let's try this one, 2016. To show that the approximation found in part C, so let me pull up the key for part C real quick, just in case we need to borrow some answers. Okay, so show that the approximation found in part C is within 0.001 of the exact value. Okay, so we got to go back to part C here. says the Taylor series for f about x equals 1 can be used to represent f of 1.2 as an alternating series. Use the first three non-zero terms. So I'm borrowing this here, okay? So the first three non-zero terms are going to be, it's going to be f of x is equal to 1. Okay. In part A, f of x was 1 minus 1 half x minus 1 plus 1 over 2 squared times 2x minus 1 squared minus 1 over 2 to the third times 3 x minus 1 cubed, and so on. Okay? That was in part A. So I assume that you guys would already have these parts, okay? So if you do have a question in the previous parts, that's a separate question, okay? All right, so they want us to approximate f of 1.2 using only the first three terms. So here we go. In part C, you should have gotten 1 minus 1 half, 1.2 minus 1, plus 1 over 2 squared times 2, 1.2 minus 1 squared, and those are your first three terms, all right? Now, in part C, I would definitely just leave this as is, okay? But for the sake of just getting a visual answer here, this comes out to 0.905, okay? Show that the approximation, so this is our approximation, is within 0.001 of the exact value. So here's what you guys do. You can just say, if you want to find the approximation is within something of the exact value, you can just say that this is your error, okay? Your error will always be less than. Now, if we use the first three non-zero terms, your error is going to be based on the next available term, okay? So if we use the first one, three terms, okay, the error is going to be based on the next available term, which is that one right there. Okay, so here we go. It's going to be the absolute value of 1, negative 1 over 2 to the third times 3, x minus 1 cubed, evaluated at, okay, so it's not really intuitive, but it's written a little bit different here. X was replaced by a 1.2. Okay? Wait, hang on. Yeah, X was replaced by a 1.2, so we're going to evaluate it at 1.2. The error is going to be, now if we take the absolute value of a negative, that's going to go away. Okay, so that's just going to be 1.2 minus 1 to the third all over 2 to the third times 3. Okay, now the cheating part is we could just say, well, that is definitely within 0.001. Okay, remember this is number 6. We don't have access to a calculator, but let me just show you guys real quick. 1.2 minus 1 is 0.2 cubed. Okay, just to show you, 0.2 is the same thing as 2/10 or 1/5. Okay, I'll do 2/10. Okay, so that's 2 to the third over 10 to the third times 2 to the third times 3. Again, I'm just doing side work just to verify, okay? This ends up being 1 over 3 times 10 to the third is 1,000. So that's 1 over 3,000. Okay. Now, back in elementary school or middle school, 0.001 is read as 1/1000th. Okay. So you know 1 over 3,000, since the denominator is larger, it's definitely going to be less than. But the cool thing is equals equal, so you don't even have to show it, but you do have to state that it is less than. Okay, so let me go over what we just did. The actual work, you have to know which term to use. and where to evaluate it. You plug it in, and you show that it's less than whatever. Okay, hopefully you guys are catching a little bit of pattern here. Okay, let's do one more. I'll let you guys do that one, 2012. Okay, this one here. I'll do all the tougher ones, okay? So again, we know it's an error because we're subtracting two different things and we're taking the absolute value of it. That's error, okay? So here, they don't tell you which test to use or which bound to use. Remember, we're either using Lagrange error bound or alternating series error bound, okay? So let me pull up 2011 so I can refer to it. 2000. Okay. Yep. Okay, so here, oh, this is not the right one. 2011 scoring. There we go. Okay. All right, so by now I assume that you have part A, B, and C done. Okay, so if you take a look at, let me pull this up for F. Okay, so by now you should already know that f of x for this problem here came out to 1 plus x squared over 2 plus x to the 4th over 4 factorial minus 121 x to the 6 over 6 factorial, and so on. Okay? This was from part B, so this is something that you should already have. Okay? If you notice here, the series does not alternate. It goes from positive to positive to positive to negative. It doesn't alternate. So if it doesn't alternate, you're not going to use the alternating series error bound. You're going to use the Lagrange. Okay? And I'm writing it here just for the sake of notes, but you wouldn't actually have to state that it's a Lagrange error bound, okay? Okay, so the Lagrange error bound is based off of the next term, okay, whether it's there or not. So here we go. So here we go up to the 4th degree. The 4th degree, okay? So the 4th degree happens to be up to that right there, okay? So right after the 4th degree is the 5th degree, okay? This is different from the alternating series error bound because alternating series, you use the next available term, which would be this, but since this is Lagrange, you use the next term, okay? So here's what you do. Since this is a degree of 4, you would use everything to a degree of 5. So your error, or in this case, I'll write p sub 4 of 1/4 minus f of 1/4. Remember, that's just error. It's going to be based on the next term, okay? So that's everything to the 5th power. So here's what you guys do. It's going to be the 5th degree over the 5th factorial, okay? At the top, you're going to have the 5th derivative, but you just put the maximum, okay? Okay. So, again, let's say this was p sub 2 of 1/4 minus f of 1/4, okay? What would you use to determine the error? Pause here, think about it. If I said that this was p sub 2 of 1/4, what would your error be based on, okay? Press play whenever you're ready. If this was p sub 2, that's the 2nd degree. After the 2nd degree would be the 3rd one, okay? So then this would be the maximum of your 3rd derivative, with your third degree with your third factorial. Okay? Lagrange, you use the next one directly, okay? With alternating series error bound, you use the next available term. So it's different. That's the only thing that's weird about it. Other than that, it's the same steps. So here we go. Oh, we'll put the absolute value bar. Sorry. Okay. We're going to evaluate this at the 1/4 that they provided for us in the error. Okay. Kind of sneaky, but it's there. So here's what happens. This is going to be less than. Okay, so you're going to plug in 1/4 to the 5th power over 5 factorial. And we have to figure out what the maximum value is for the 5th derivative when we're close to 1/4. Okay, they conveniently gave us a picture of the 5th derivative. All right, so let me draw some arrows here so you can see. The maximum of the 5th derivative is shown in this graph right here. At 1/4, 1/4 is right there. So that right there, we don't know the exact answer. But what's the most that it could be? We know that it can't be anything more than 40. So it's definitely less than 40 there. Okay? So we're going to say that the maximum is 40. All right? Okay? And again, we can cheat and we could say, and we know that that's definitely less than 1/3000. Okay? We could show the work, but equals equal. But you have to state it. If they're asking you to show that it's less than a value, you have to state it. Okay? Do I have another Lagrange? Let me see. Yeah, that's it, you guys. I encourage you guys to practice the ones that we didn't cover because that's the only way you're going to get good at it. So, again, remember, Lagrange error bound is the next term right after, okay? So if you're approximating with the 5th degree, then you're going to be using the 6th degree, whether it's there or not, okay? With the alternating series error bound, you're going to use the next available term. So that's as complicated as it gets. Hopefully from here, you kind of get an idea that you only have to show about maybe 2, 3 very tiny steps to get 3 to 4 points there, okay? So again, practice. You guys are going to kick butt on the BC exam because you're so well versed in series, okay? So practice. Text me if you guys have questions.